Okay, let's look at the homework 13, problem number 1 example. All right, so I'll do a similar problem here. So we have a mass spring system, and you have 3 springs and 2 masses like that. And the displacement for the first mass is x, and the displacement for the second mass is y. All right. So we're looking at the characteristic mode of vibration. So we can let the x2 be x0 e to the iwt, and y equals y0 e to the iwt. Right? So x and y has the same frequency. Right? By taking a second derivative with respect to time, we can get this. Right, so if you take the derivative of x with respect to t twice, you can get, right, you're going to get the negative w squared just x, right? And the same thing with the y, so y double prime is going to be negative w squared y. Right? Then we can look at the spring potential for the whole system. So we're going to look at spring potential for each one and add them up. Right? So spring potential V is equal to, right? So it's 1/2 times the spring constant and displacement squared. So the first spring, it's just going to be 1/2 spring constant K. Then displacement would be x squared, right? And the second spring, the same way, 1/2. Spring constant is same k, but the displacement is going to be the difference between x and y. So it's just a quantity, x minus y squared, right? And the spring potential for the third spring would be 1/2 k, right? So displacement is y, so it's just y squared, right? So if you multiply it out, let's see, everyone seems to have k over 2, so I'm going to just pull those out, k over 2, right? And you have x squared from the first spring. Right, from the second spring, I'm going to just multiply out, so that will be x squared minus 2xy plus y squared from the second spring, and last spring is going to be just a y squared. Right, so this is going to be k over 2. Right, so there are 2 x's, so you have a 2x squared. Right, then you have a minus 2xy. Right, then you have 2 y squared, right? And we can cancel, let's see, everyone has 2, so I'm going to just go ahead and cancel 2 here, 2 here, 2 there, 2 there, canceled out. Then you get just, this is going to be k times x squared minus xy plus y squared, right? So we have that, right? Then we have to somehow relate the spring potential and maybe the force. And remember that force, I'm going to write it here. So force F is, as we know, mass times acceleration, right? For the spring, it's negative kx, right? And we can relate this guy with the spring potential. This is going to be simply negative partial derivative of the spring potential V with respect to x, right? So let's do that. So we're going to look at, let's see, force. Force on the first mass. I'm going to say mass number 1, right? So this is going to be, right, so mass times acceleration. Acceleration is the second derivative, so we have m right? And acceleration x double prime would be negative w squared and x, right? And this is equal to, right, negative of the partial of the spring potential with respect to x. So I'm going to just put that negative partial of v with respect to x. All right, so let's do that. So you have a negative k, just a constant multiple, right? So partial of this with respect to x is going to be simply 2x minus y, right? And we do the same thing with the force on mass 2. So I'm going to do a force on mass number 2, right? So in this case, displacement is y, so we're going to do a negative mass times acceleration is equal to, now we have to take the partial of the spring potential with respect to y, right? So this is going to be, so you have a negative sign, and a k is a constant multiple here. So partial of this guy with respect to y, you're going to get, let's see, that's 0. So that's going to be negative x and plus 2y, right? So we're going to combine this, and since both of these guys have negative k, so I'm going to just go ahead and divide by negative k. So you will get this, right? So both of these guys, negative sign is cancel out. So you have mw squared over k. So I'm going to factor that out. So mw squared over k, right? So you have x and y. So I'm going to write it in a matrix notation. So here's x and y, right? And this is equal to, right? So negative k is gone. So you have a matrix. So I'm going to just write down the coefficient. So you have a 2, negative 1, negative 1, and 2. Right? Then you have a variable x and y, right? And you should convince yourself that this matrix equation is exactly the same equation as this pair of equations here. All right, then you notice that if you look at this expression as the eigenvalue, so say lambda, right? So this is an equation we need to satisfy when you try to find the eigenvalue. So let's find the eigenvalue of this guy, right? So eigenvalue of this matrix, right? So we have to do a determinant 2 minus lambda, negative 1, negative 1, 2 minus lambda, right? And this is going to be, let's see, this times that is going to be lambda squared minus 4 lambda, right? And plus 4, then you have to minus 1, so it's going to be plus 3, right? So we can factor this out as lambda minus 1 times quantity lambda minus 3, right? We set this guy equal to 0. You will get lambda equals 1 and lambda equals 3, right? So we have that, right? Then so from these lambdas, lambda values, we can find the characteristic frequency, right? So let's do that. So since so when lambda equals 1, right? So mw squared over k is equal to 1. So that's the lambda value. So we can just multiply by k over m to get w squared is equal to k over m, right? Then take the square root of both sides. We get w is equal to square root of k over m. Right? Since W is a frequency, we only consider the positive one. If it's negative, we just go in the other way around. So we just have that. So this is called the characteristic frequency. Right? This is characteristic frequency. All right. And then we can describe the characteristic mode of vibration by plugging in the eigenvalue back in here. So 2 minus 1 is 1, so 1x, so x minus y equals 0, right? In other words, you can probably write it as, y equals x, right? So this means that with this frequency, x and y are exactly the same. So that means that these two masses, go back and forth, left and right, go in the same direction with the same magnitude back and forth. So the same way here, all right? For the other eigenvalue, lambda equals 3. Right, so if you do that, then you're going to get mw squared over k must be equal to 3. Then we can solve for, so multiply by k over m again. So w squared would be 3k over m. Then taking the square root of both sides, we get w equals square root of 3k over m, right? So this is a characteristic frequency, and in this case what happens is plugging 3 back in here, so you're going to get the negative x minus y equals 0, which gives you y equals negative x, right? So because of this negative sign, these masses move in the opposite direction with the same amplitude. So it gets closer and back and forth, and x is move in the opposite direction, right? And you can see that the frequency is a little higher that way than when you have two masses moving in the same direction, right? So these are the modes of vibration, and these are called characteristic frequencies. All right, that's it. I hope that this was clear.